Hi everyone, welcome back to Math 261. This is Scott. Let's get started. What we are now doing is we are building to a crescendo for the exciting conclusion of Math 261. So this is our penultimate section, 6.5. And in section 6.5, we're going to look at how some of the things we've been talking about lead us to what are called least squares solutions. So this is least squares problems. So in the next section after this, what we're going to be doing is actually looking at how this gets applied in a number of different, more realistic scenarios. But for now, what we're just going to do is work out the process. So this is effectively the last process you're going to have to learn in the main body of this course. So buckle up, because it's going to be a wild ride. So here's the idea. So in real life systems, there are frequently no exact linear solution solutions to the problems. And that's either because the situation is not actually, literally, a linear one, or it's that maybe the data that we're using in the situation is not from some exact thing, but is rather from some sort of a measurement, and all measurements carry with them the possibility of some sort of error. So that means that our goal is going to be to find not necessarily the solution, but the closest solution. So when a linear system is inconsistent, we can still find a closest solution. Solution. All right, now what does closest mean in this case? So here's the setup. So what we're going to have is AX equals B. Now this is the most classic setup we've had in this class, so this is just regular linear algebra looking stuff. Here's the catch though. Where there is no solution, X. Okay, well, seems like then, case closed, nothing we can do here. Wrong. So then, the least squares solution to this situation will be this. So x bar, sorry, x hat, I mean x hat. So x hat such that the magnitude of b minus a x hat is less than or equal to the magnitude of b minus a x for all x in Rn. Well, we've seen this before, but let's try to remember how we actually can get such a thing. So if you remember, this was also what we noticed about the orthogonal projection of a vector onto a vector space, and in particular, let's think about this. So finding x hat. So b hat. So this is going to equal the orthogonal projection, the projection onto the column space of A of B. So what we've got here now is the closest point that actually is in the column space of A to the B that we're trying to hit. So if this actually had a solution, we would be looking, then B would be in the column space of A, and we'd be looking for how to get there. Now if there is no solution precisely, then what that means is we're looking for the closest approach to it that we can get, which would be the orthogonal projection onto the column space of B. So then x hat is the solution, or a solution, to ax hat equals b hat. Alright, well let's think about what that actually means then. So if we're talking about the orthogonal projection of B onto the column space of A, then that means that the orthogonal complement will be orthogonal to the column space of A. But the orthogonal complement, Z, which is equal to B minus B hat, so it's the orthogonal complement, is orthogonal to column space of A. So therefore, so orthogonal to the column space of A, that, if you remember, is related to the null space in the following way. Therefore, since column space of A perp, so the orthogonal complement of the column space of A is equal to the null space of A transpose, then that means that B minus B hat, so vector B minus the orthogonal projection of B, that means this is in the null space of A transpose, which means that there is a solution, or actually, sorry, which means that A transpose times B minus B hat is equal to the zero vector, which in turn means that, because matrix multiplication here is distributive, which means that A transpose times B minus A transpose B hat is equal to the zero vector, which if we add this to both sides, it'll give us A transpose B is equal to A transpose B hat. And if B hat is equal to A times X hat, then that means that A transpose B is equal to A transpose times A X hat, which means if we rewrite this in the other direction, A transpose A X hat is equal to A transpose B. Now, this now actually involves only pieces that we were given from the very beginning of our setup, and then one piece here. So this is called the normal equation, or actually it's technically called the normal equations, because it's a system, and in statistics they would typically think of this as being more than one equation. We might think of it as being just one vector equation, but they think of it as multiple equations. And so this system of equations is called the normal equations. And normal equations for ax equals b, and the solution is the least square solution. And its solution, x hat, is the least square solution. Now, a word on the name. The reason why it's called least squares is because the way we are defining the distance in this particular vector space is by taking the square root of the sum of the squares of the entries. And so it's the this is the value that minimizes the sums of those squares, and so it's called the least squares solution. So now let's actually give this a try. So as an example of this in play, let's take this. So what we're going to have is A, which equals 1, 3, 1, negative 1, 1, 1, 1, 2. We're going to take a B, which equals 5, 1, 0, 3. And now what we're going to do is we're going to work our way through this. So A, construct the normal equations. For ax equals b. Alright, well, looking at this, the normal equations, so those involve A transpose A, and this mystery x hat, is equal to A transpose B. So what we just have to find is this, and that will be a construction of the normal equations. Alright, well, A transpose A will just be, if you recall, you just turn the matrix on its side. 1, 1, 1, 1, 3, negative 1, 1, 2 times. And as you saw last section, you calculators also know how to take transposes. So 1, 1, 1, 1, 3, negative 1, 1, 2. Alright, so this will be 1 plus 1 plus 1 plus 1 equals 4. This will be 3 minus 1 plus 1 plus 2 equals 5. This will be the same. A times A transpose, this entry and this entry will always end up being the same, just for reasons that I hope you can figure out. And then here, we're going to have 3 times 3, plus 1 times 1, plus 1 times 1, plus 2 times 2. So that adds up to 15. So that's that part of it, and then we need the A transpose B. So now we do again 1, 1, 1, 1, 3, negative 1, 1, 2, and now it's times B. It's going to be 5, 1, 0, 3. You can use a calculator on this, or you can just calculate it by hand, and it's going to be 5 plus 1 plus 0 plus 3, so that adds up to 9. And then down here, we're going to have 15 minus 1 plus 0 plus 6, which adds up to 20. Alright, and then so the normal equations here are going to be if we wrote it out as a system, it would be 2 equations. That's why they're called normal equations. But if we write it as a matrix, it would only have the form of 1 equation. So 4, 5, 5, 15, mystery x hat equals 9, 20. Alright, now to actually solve this, we can solve this by a number of methods. We can set up the row reduced, or we can set up a row reducing augmented system and go from there. Or alternatively, we can solve it by something like you could use Cramer's rule, or you could use the inverse matrix to this and multiply because it's only a 2 by 2. But no matter how you do it, you'll hopefully get the same result. Which is, if you row reduce, you'll get 1, 0, 1. So I'll leave it to you to verify this. So you will reduce this and you will get this, which then leads you to x1 equals 1, x2 equals 1. So that means that x, oh, sorry. So that was us getting ahead of ourselves. All we had to do was construct the normal equations in part A. Part B, that'll be solve the normal equations. So solve couldn't help ourselves. Once you set up that equation, you just can't help yourself. You just want to solve it and find x hat. Solve to find x hat. So then x hat will be 1, 1. Okay. So that's how that can go. Now a note about the way this can end up. So here's the theorem. There we got a unique solution, a unique x hat. That will happen sometimes, it will not happen other times, and what makes the difference is the matrix A. In particular, let's say that A is m by n, not square, m by n, Mike by November. the following are equivalent, meaning they're all true together, or they're all false together. Oops, equivalent. All true or all false? Okay. A. There is a unique solution, a unique least square solution, as above. The unique least square solution to ax equals b for each b in Rn. So that's what happened in that example above. There was a unique solution. When we row reduced it and all, we ended up with just getting a 1-1. Now, what that basically amounts to, according to the setup of the normal equations and the invertible matrix theorem, what that amounts to is the same thing as saying that A transpose A is invertible. But as we saw in the previous section, that in itself is equivalent in turn to the claim that the columns of A are linearly independent of each other. Columns of A are linearly independent. And we saw that when we were discussing the QR factorization of the of a matrix, and that requires that the columns be linearly independent, meaning that the basis for the column space is actually the original columns. And then according to Gram-Schmidt process, we can construct an orthonormal basis for the same column space, and those make the columns of Q. And then we can find R, which is an upper triangular matrix with all positive entries along the main diagonal, such that Q times R equals A. So when these are true, then we can actually come up with just a little formula for x hat. So if you look at the normal equation, A transpose A times x hat equals A transpose times B. So we just multiply by the inverse that the theorem says we would have. So A transpose A inverse times A transpose times B. So when these are false, we get a parametric family. Of least square solutions. So this is what happens if the columns of A are not linearly independent. Then you don't get a unique solution, which we could boil down into a succinct formula like this. We get a parametric family. So let's see an example of something like this. So an example of a parametric family of solutions would come from something along these lines. So find all least squares solutions to x equals b for A, which is going to equal, so reading across the rows, 1, 1, 0, 1, 1, 0, 1, 1, 0, and then the next three rows are going to be 1, 0, 1, 1, 0, 1, and 1, 0, 1. And then let's say B, doesn't matter what B is because we can already tell actually that these columns are not linearly independent. I can easily see that column 2 plus column 3 would equal column 1, but that's just there for the noticing. If we want to do the calculation, we have to work it out, and so we'll need a B. So B is going to be 7, 2, 3, 6, 5, 4. 7, 3, 2, 6, 5, 4. Okay. So unfortunately now, since we do have this linear dependence, we're not going to be able to sum it up in some succinct formula like this. We're going to have to find the normal equations and work our way from there. So A transpose A times X equals A transpose B. This is home base for us. This is the position that we are always going to be in. So let's now figure out the pieces that go into this. A transpose A, that's equal to 1, 1, 1, 1, 1, 1, 6 ones. And then the next one is going to be 1, 1, 1, 0, 0, 0. And then 0, 0, 0, 1, 1, 1. In turn times 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2, 3. 1, 2. Sorry. 0, 0, 0, 1, 1, 1. Alright, and then just multiplying these across, I can see it's going to be equal to 6. When I do that, it's going to be 3, and it's going to be 3. And then here, it's going to be 3. It's going to be 3, and then it's going to be 0. And then here, it's going to be, looks like 3. It's going to be 0, and it's going to be 3. Alright. Now for A transpose B, that's going to equal 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 1 times 7, 2, 3, 6, 5, 4. So the first entry is just going to be the sum of all these. So 7 plus 2 plus 3, so that's going to equal 12, 18, 23, 27. This is going to be the sum of just the first 3. So it's going to be 7 plus 2 plus 3 is 12. And then this is going to be the sum of just the last 3. 6 plus 5 plus 4 is 15. Alright, so then that gives us our normal equations, which now do not correspond to a situation where we've got a unique solution. They're going to correspond to a parametric family of solutions because we're going to have, when we row reduce, a row of zeros at the bottom, courtesy of the linear dependence of these columns. 7, 12, and 15. So this is where we are, and we row reduce. And when we do, I'll leave it to you. It's a matter between you and your calculator to find out. But you can confirm, hopefully, that it'll be 1, 0, 1, 5, 0, 1, 1, negative 1, negative 1, and 0, 0, 0, 0. So the normal equations, by the way, they will never be inconsistent. They're what we produced in order to make the system consistent. They, in turn, won't ever be inconsistent. They are always going to be it's always going to be consistent. It just if the columns of A are linearly independent, it'll be a unique solution. If not, it will be a parametric family of solutions. Okay, so now if we think about this, x1, x2, x3, so x1 plus x3 equals 5, which means that x1, alright, so which means that x1 equals negative x3 plus 5, and by the same token, if we have x2 minus x3 equals negative 1, then that implies x2 is equal to x3 minus x1, which then, because x3 is free, will give us our third equation, x3 equals x3, which will give us then that x, which was actually x hat in this case, because that's the modified system that we're actually solving, it can be anything of the form x3 times negative 1, 1, 1, plus 5, negative 1, 0. Where x3 is completely free. Okay. Now, when we have found, so when we have x hat we can find b hat, and that was, remember, the relationship between them, b hat equals a x hat. So x is the closest x there is to solving the equation, and b is its best attempt at actually getting a solution. So then the least squares error is equal to the magnitude of b minus b hat. Now let's actually try an example where we will find the pieces. Okay. So we need to have a matrix, and we need to have a B. So let's say A is equal to, so I'm going to go down the first column. 1, 1, 0, negative 1, 1, 0, 1, 1, and then 0, negative 1, 1, negative 1, and then B, so it's not B hat, just regular B, it's going to equal 2, 5, 6, 6. Alright, so the very first question will be A. Find the orthogonal projection of B on the column space of A. Alright, well, let's think about this. So, B. Or actually, the way I would word this is projection onto column space of A of B. That's what we call B hat. So that's what we're actually that's what this is actually asking us to find. And so that involves finding the x hat and then multiplying by A. So to find the x hat, what we need to do is look at A transpose A. The normal equations are our starting place for all these calculations. So A transpose A, so it's going to be 1, 0, 1, 1, -1, oops, 0, -1, 1, -1, okay, times, and then here we have 1, 1, 0, -1, 1, 0, 1, 1, and then 0, -1, 1, -1, which is going to equal here, looks like 3, and then this next one, it looks like is going to equal just 1, and then the next, or actually, I mean 0, 3, 0, and then this next one is going to equal -1 plus 1 is 0, and then here we're going to have 3, or sorry, 0, I mean, and then 3, and then here it's going to be this one times this one, 0, 0, -1, 1, 0. And then lastly here we're going to have 0, 0, 3. Alright, and then as for A transpose times B, that's going to equal 1, 1, 0, -1, 1, 0, 1, 1, 0, -1, 1, -1 times 2, 5, 6, 6 is going to equal, so it's going to be 2 plus 5 is 7, minus 6 is 1, and then here we're going to have 2 plus 6 equals 14, and here we're going to have -5 plus 6 minus 6, oops, it's going to be -5. And so what we have here is 3, 0, 0, 0, 3, 0, 0, 0, 3, augmented by 1, 14, and -5. And I think we can all do this row reduction hopefully in our heads. It is practically in our REF already. All it needs is some scaling. And so with the necessary scaling, we're going to have 1, 0, 0, 1/3, 0, 1, 0, 14/3, and 0, 0, 1, -5/3. And so that gives us an x hat of 1/3, 14/3, and -5/3. But that's not what the question was asking. The question was asking us for the orthogonal projection of B on column A. So B hat is equal to A x hat, which equals So we got the 1, 1, 0, negative 1, 1, 0, 1, 1, 0, negative 1, 1, negative 1, times 1/3, 14/3, and negative 5/3. And so when we actually calculate that out, what we get is going to be equal to, so that's 1/3 plus 14/3 is 15/3, so that's in other words 5. We have 1 plus 5/3 is 6/3, so that's going to equal 2. And then what we have is 14/3 minus 5/3 is 9/3, which is 3. And then here we have negative 1/3 plus 14/3 plus 5/3, so it's going to be 18/3, which is 6. So 5, 2, 3, 6 is, I believe, the answer. So this is the orthogonal projection of B onto the column space of A. And what that means is, out of all of the points in R4 that you can make out of the columns of A, this is the one that you can make that's closest to this one. Now, how close is it? Let's find out. Find the least squares error. Well, magnitude of B minus B hat. So that's how close this is how close we can come to this particular B using these columns of A. So that's going to equal the square root of, and it's just going to be the differences between the two. Or actually, let's write it in a couple steps. Just remind us all what we're talking about here. So B minus B hat is equal to 2566 minus what we just found, 5236, which is equal to negative 3330. And then the magnitude of that, so B minus B hat, be square root of 9 plus 9 plus 9 plus 0. So that's going to be the square root of 27. Which there's no, you could pull out the root 3 and simplify that if you wanted, but there's no advantage to doing so, and so we won't. Alright, now let's bring the QR factorization into play, and in particular this is an alternative way to find the x hat. Alternative method for finding x hat, and it's using the QR factorization. So if A has QR factorization of A equals QR, where Q is, as we said, orthogonal, and R is upper triangular with positive entries along its main diagonal. So Q is orthogonal, and R is upper triangular positive entries on main diagonal. Then A transpose is equal to QR transpose, but the transpose of a product of two matrices is the same as the matrices in reverse order transposed, which means then that A transpose A times x hat is equal to A transpose times B. This can then be rewritten as R transpose QT or Q transpose x hat. Oops. I meant to say, so that's A transpose A. So that's R transpose Q transpose times Q R times x hat is equal to R transpose Q transpose times B. Now Q transpose Q, because the columns of Q are orthonormal, this makes just the identity. Q transpose is, if Q is square, in fact the inverse. If it's not square, then we don't quite say inverse, but it is basically the same thing. And so this gives us R transpose R times x hat, R transpose QT times B, and R transpose R is invertible because R is invertible, and so then if we multiply both sides by R transpose inverse, that'll be R x hat is equal to QT B hat. So R transpose is invertible. So we can basically cancel it out from the left on both sides by multiplying on the left by R transpose. And then R is also invertible. Which means finally we get the solution here, multiply both sides on the left by R inverse, and we'll have R inverse QTB. And this is a way often in certain statistics settings the solutions will be found here. For us though, it's just an interesting exercise, so let's give this a try. Now for this, I'm going to give you the QR factorization to begin with, so we don't have to go through all that rigmarole. But if you didn't already have the QR factorization, you could find it using the Gram-Schmidt orthogonalization process. Okay, so A is equal to 1, 1, 1, 1, negative 1, 4, negative 1, 4. And that happens to also equal 1/2, 1/2, 1/2, 1/2. So this is the Q that we're making right here. Negative 1/2, 1/2, negative 1/2, and 1/2. So that's Q. And then here comes the R, 2, 3, 0, 5. And then let's say that B is equal to -1, 6, 5, 7. Now, we needn't have been told this Q and the R. We could have actually used the process from the previous section, the Gram-Schmidt orthogonalization process, to have found it, but if we have it, there's no use looking a gift horse in the mouth, and so let's go ahead and use it. So now our goal is to find x hat. So there's the problem, so now let's find it. Alright, so x hat is equal to R inverse Q transpose B. Alright, well, let's find R inverse. So R inverse. This is a little 2x2 matrix, and so it's not too hard to find its inverse. Just find the determinant. So 1/10, so 1 over the determinant. And then here you just switch the A and the D, so 5 and 2. And then you make the C and the B and the C each negative, or they're opposite anyway. So it's that, and then we'll just write this as 5/10 minus 3/10, 0, and 2/10. Now, because of what we're about to do, it's easier if we don't actually reduce this, although we see that we can. We're about to do some computation, so it's often easier if everything has a common denominator than otherwise. So then x hat is going to equal 5/10 minus 3/10, 0 and 2/10 times, and then here the Q transpose is going to be 1/2 all along the first row, and then on the second row it's going to be alternating -1/2, +1/2, -1/2, +1/2, and then times B. -1, 6, 5, and 7. Okay, so now then we just roll up our sleeves, or we unsheath our calculators, and we get to work. So, let's see. So these are, that multiplying by halves is just going to turn all tenths into 20ths. So what we'll have is 5/20, in fact, plus 3/20. This is going to make 8/20. In other words, no, I'll just leave it as 8/20. 8/20. Okay. And now let's go, so here we're going to have 5/20 minus 3/20 is going to be -2, sorry, it's going to be, 5 minus 3 is going to be 2/20. Okay. Here that's going to be the same, 8/20. And it's going to be the same as that one, 2/20. And then down here, we're just going to be doing, it's going to be -1/10. It's going to be 1/10, -1/10, and 1/10. Times -1, 6, 5, and 7, which we can then proceed here. So it's going to be for the first one, just looking at the numerators, -8 plus 12 plus 40 plus 14. So -8 plus 12 is 4, plus 40 is 44, plus 14 is 58 And then here we're going to have 1/10 6/10 minus 5 plus 7. So in other words, it's just going to be 1 plus 6 minus 5 plus 7, and that's going to add up to 9/10. And so if we reduce this a little bit, we're going to have 29/10 over 9/10. So that involved actually just some admittedly tedious computations of matrix products, but no fancy solving of any kind. All right. Well, that'll be a good place to end it. In the next section, which will be the last section of this course, we will look at how these least squares problems lead into linear models for a variety of situations. So stay tuned for that. Until then, thank you for joining me for this episode of Math 261. Bye.